Hi, everyone. I'm delighted to welcome fellows and visitors to the first discussion meeting of the 2026 session. We will be discussing the paper Regression by Composition by Farewell and co-authors. With grateful thanks to Imperial College London, this Royal Statistical Society discussion meeting is being held here, where it also welcomes an online audience, so we're hybrid. If you're online, please keep microphones muted and cameras turned off unless called to speak during the open session later. A recording of the meeting will be posted on the RSS YouTube channel. If anyone prefers not to be filmed, just let us know and we can edit that part out. If you experience technical problems online, then use the chat box. We actively encourage everyone to contribute to the discussion of the paper in the open session later, both in person and online. Comments or questions can be brief or up to 5 minutes long. Anyone who has given their name in advance will be called first. And then all comments can be written up afterwards, around 400 words, and will be published in the journal Series B along with the paper. The paper will be presented by Daniel Farewell and co-authors, Rian Daniel and Mats Stensrud. It will be published in Journal of the Royal Statistical Society Series B in 2026. Daniel will speak first for around 20 minutes, followed by Rian for 10 minutes, and Mats for another 10 minutes for 40-minute overall for the presentation. So I'd now like to call Daniel to present the paper. A recording, 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 a recording.
I'm going to stand over here again. So thank you for the nice welcome, Adam. A few more thank yous right off the bat. First of all, most obviously to the Royal Statistical Society for this opportunity to share our excitement with you, and to you all in person and online for making this a special occasion. It means a lot to us.
A recording.
Big thank you to the referees, some of whom immediately got it, but no less thanks to the people who rightly said we didn't yet got it. All of this was incredibly helpful to us and continues to stimulate useful thinking. The next group of people there all read drafts at various stages of progression and gave comments. I want to mention Yassine in particular, who sort of put us back on the right track with regard to collapsibility. It was a big contribution. My good friend Mark, we've had some really helpful conversations around multiplicative comparisons. So useful. Tim and Ruth gave us a puzzle to solve. William and Catherine gave us some data to analyze. Tim helped us understand growth modeling, and our friend and colleague in Cardiff, Simon, helped make the R package possible. Without all of these people, and of course many more, this would not have been possible. So I'm going to speak, as Adam said, for around about 20 minutes, if all goes to plan. Then Fian for about 10, and then Mats for about 10. I'm going to talk theory, roughly speaking. Fian's going to talk applications, and then Mats will take a step back and give us a bit of a where are we overview. But I want to mention at the outset the one author that you, oops, sorry, this is not yet clicking. I will make that happen.
A recording, a recording, a recording.
The one author you won't be hearing from up front, Anders Whitfeldt, is here in the room. The reason Anders needs a special mention is because this work began 5.5 years ago when Anders sent us an email with a complete draft manuscript outlining a new approach to binary regression. And although we didn't quite realize what we got, in retrospect, I can tell you that almost all of the key ideas we will talk about today were there in some form already in Anders's original draft. I'd like to try and prove that to you. This is early on in the draft that Anders sent us. There was already a notion of a pipeline of transformations, and Anders already had this notion that we're going to have a probability input and a probability output. And crucially, that the properties of those transformations will tell us about statistical features of the model. For example, if whenever you have a probability in, you get a probability out, then the model is in a certain sense sound. And that isn't the case for all statistical models. And we'll come to some examples in a minute. So that's an important sort of closure property that some models locally have. Also, the idea that if those transformations taking probabilities to probabilities are affine, so straight line functions, then the implied comparison of distributions is going to be a collapsible one. And again, we'll come to what we mean exactly by collapsible in a moment. So this idea was already there in the original draft. Anders, I just wanted to say on behalf of the rest of us, it's been an absolute pleasure and privilege trying to formalize some of these ideas and to continue working with you. The paper begins with just an attempt at some familiar examples to kind of ground what a regression by composition perspective looks like on regression models. So here's the basic idea. We're going to build the standard normal regression model, and we're going to do that by starting with a standard normal distribution. So mean zero, variance 1. And we're going to then, this pipeline should be sort of understood a bit like a Unix pipe. So what are we going to do next to that? Well, we're going to scale it. So we're going to allow that distribution to become wider or narrower. And then we're going to translate it. So wherever we scaled it to, we're then going to shift it along. And one idea is that we're going to allow covariates to tell us how much we scale or how much we translate in this case. Now that should be pretty familiar to many people, but one feature of this is that this scaling transformation or the translations should in principle be able to accept any distribution. So although we've started with a normal distribution, we didn't have to. And the way that that gets characterized is this way. We're going to say that scale, we're going to call it a flow in a minute, that scale flow, well, it sort of acts on a cumulative distribution function. This is one way you can write it. So if you like, the capital F is the input cumulative distribution function. And I'd like you to read f dot v to be that cumulative distribution function, the input, acted on by some vector v. And that's the output cumulative distribution function. And you can see that the way those two are related is exactly this scaling property. And that's why we've sort of called this family of transformations a scale. Now, it's very common that statistical parameters will have some sort of set of values that is somehow allowable, right? That's a very common feature. What's maybe a little bit less common is to indicate how those values combine with each other. So this scale parameter, v, needs to be a positive number, but there's also a sense in which the way they combine is multiplicative. That's maybe less usual to emphasize that, but it is going to be an important feature of the way that we set up these models. And then probably more obviously, again, if you accept any old cumulative distribution function, well, you can see how, kind of from GCSE mathematics, you can take that function and shift it along. I remember always getting confused with the sign here. Is it a plus or a minus? And we still have to check sometimes. This is a real number action. So these things combine additively, as you might expect. Both scaling and transformation translation are examples of transformation models. It's a very powerful, flexible class of models. Hawthorne and co-authors have written about this. It's not the only kind of flows, but it is a very helpful one. I mentioned that we don't just have to think about covariate effects on, if you like, on the location. So we can, for example, allow, say, older people to have wider or narrower distributions. So just read these things in the brackets as a little bit like the sort of usual R formulae, if that's helpful to you. So there's nothing wrong with modeling the scaling as a covariate effect as well.
No. Yeah, I'm just how she's on finished.
A recording.
Already got commentary. It's great.
Recording.
more interestingly, you don't have to start with a normal distribution. And this is really where you start to appreciate why it's useful that these things can take any old distribution. So imagine you started instead with a standard uniform distribution on the unit interval. Well, again, that can be fed into this pipeline of families of transformations. So now, in a sense, what you have is a parametric family not parameterized by its standard deviation and its mean, but by its width and its minimum. It's still scaling and transformation in both cases. Or we can add in other building blocks. This is our name for what Jones and Pusey call hyperbolic scaling. We've called it cinch. It's sort of, it lightens or heaviens the tail, weightens the tail, that's probably a better word. But it's a little bit like belt tightening. So with reference to the hyperbolic sign, we went for cinch. So here we have a 3-parameter family of parametric distribution, parametric family, where any or all of them are amenable to covariate modeling. Okay, I'm going to show you the same idea in a binary setting, but for people who prefer thinking visually, we're going to go for some pictures. So we're going to start with logistic regression, familiar to many, probably not exactly written like this, but I think you won't fail to recognize it in a second. So logistic regression starts with a fair coin toss. And then, according to treatment, we'll scale the odds of a head by a certain amount. So it's a sort of one-flow regression by composition. So what does that look like? Something like this. This is what's known as a Labbé plot. Roughly speaking, read the input probability on the horizontal axis and an output probability on the vertical axis. The family of sort of available transformations is represented by these colored lines. So, for example, let's imagine that there's 4 groups in our study here. The 2 kind of top lines there are going to be the older people, and the 2 bottom ones are going to be the younger people. So what we've got going on here is that this line starts at 0.5, so the midpoint. It's chosen pretty much arbitrarily, but we'll start there. So for the older people, what happens is that we quadruple their odds. That's the yellow line at the top. And so we see that we read off their new probability there. But for the treated older people, it's only a doubling of the odds. For the younger people, the dotted line, they actually have half of the odds relative to 0.5. And for the younger treated, well, it's half again, so a quarter of the odds. So we have those odds have been scaled in different ways according to the covariate groups. Okay, so we've sort of mentioned this already, but we could, if we wanted, separate out the treatment effect into kind of a separate family of transformations. It's the same one, but let's conceptually separate it out. So what you're going to need to do to understand what's going on here is kind of for the top left quadrant, you're kind of imagining tilting your head to the left. So you're now reading the vertical axis as the input probability and the negative horizontal axis as the output probability. This will make more sense once I put up the lines. So what we've got here is that, remember, the older group quadrupled their odds, but then the treated ones of those, which is the dashed line, they got halved. So that top left corner is capturing the effect of treatment, if you like. Now you can see that the output probabilities are no different. We've just conceptually separated out those 4 groups into 2 panels of 2. Okay, so far so straightforward. Really, one of the key ideas that Anders brought to us was, well, what if we just use a different family of transformations in that second quadrant? So what if treatment doesn't work the same way as age does? Well, you can see that in this picture, there's no reason not to think about that. So now what we have, again, is that the older people have their odds quadrupled, but now the treated people among them have their risk halved. So we read that. And you can see that that is a materially different model to the one where, in both cases, the odds was being scaled. So it could be better, it could be worse, but it is different. Once you get to this point, you realize, well, the sky's the limit. What about if instead of scaling the risk, you scale the complement of the risk? So again, you're sort of looking at this picture on its side still. Oh, but why not do both? Okay, so now by the time you get into the bottom left, I'd invite you all to stand on your heads, but that might be dangerous. But you'll see the idea immediately. So let's follow the older group again around. Starting at 0.5, quadruple the odds. So in this case, what we've got is that the complement of the risk in the treated group actually goes up, it's doubled, but then the risk is halved in the next group. The same thing happens in the younger group. So the initial odds are halved relative to 0.5. The treated group gets that complement of the risk doubled, and then the risk halved. The feature that you should observe about this is that what we've got is actually that treatment is beneficial in the older group, but harmful in the younger group, interpreting this in a sort of broad sense. And the reason that might be a surprise is because nowhere in the sort of covariate specification was any what you might think of as an interaction term specified. So that interaction has been enabled by the composition of 3 families of transformations. So it's an interesting and different way to capture a qualitative interaction. Okay, let's try and be a little bit more formal now. When we think about these families of transformations, we need them to satisfy certain properties. It's really helpful when we can keep these things under control. So the way I'd like you to read this, P is a distribution, and it's acted on by a vector V. So P dot V, it's not multiplication, it's the action of a vector V. We write it on the right. That's basically because it's convenient to read left to right. There's nothing material about that. It's just convenient to do so. This vector space action has 2 really quite natural axioms in a regression context. The first is that if you have a distribution and you act on it with the identity element, you don't go anywhere. This feels very natural. It also feels very important because in a regression context, you want to be able to capture the idea that this covariate is really unrelated to the outcome of interest. So that ability to capture that, albeit a basic one, is an important requirement. And the second is probably no less important. It's capturing a kind of homogeneity, the way that the regression model simplifies the way effects add up. So the idea here is that if I start at a distribution P, and I act on that by V, and then by V prime, well, that's just the same thing as starting at V and going directly by V plus V prime. And this is a compatibility axiom that allows us to understand these groups of transformations in a consistent way. Both of them are very natural in a regression context. And so I guess it's not a surprise that these ideas have been around for a while, dating back at least to Fraser's ideas of structural inference, but also Barndorf, Nielsen, and McCullough have been writing about these things for quite some time, and with good reason. One of the reasons that Anders highlighted for us that studying these groups of transformations might be helpful is because they reveal features of the statistical model. Here's one way they do it. This is the notion of an invariant set. So just imagine S is a set of some distributions. And what we'd like to know is, starting anywhere in this set, and then acting on that set by any element of the vector space, where can we get to? That's what I mean by S dot V there. Where can we get to if we start from somewhere in this set? If we can't get anywhere other than the starting set S, that set S is known as an invariant set. And here's how that links to some stats properties. If that set is just a single point, a single distribution, and no matter how hard you try, no matter which element of the vector space you act on it by, you don't move from where you were, That's called an invariant point, or a fixed point. Deeks writes about this and calls them zero constraints. So basically the model is constraining. Imagine that it was a treatment effect you were modeling. The model is constraining us to have no effect on this point. The treatment, no matter what it is, will not move this point. So if you like, that's a pretty inflexible part of the model, at least locally.
A recording.
Here's another example. We've written, so among the set of distributions that I'm talking about, some of them actually have probabilities that are either bigger than 1 or less than 0. So we've identified a special subset triangle.
A recording.
And if that subset of triangle of probability distributions stays put, so to speak, so no matter how you act on the probability distributions, you stay at a probability distribution. If that is an invariant set, well, then you're in a setting where, again, the model is sound. There's a good local soundness. So I'm going to contrast two here. The Cox model is a good example of a model that is closed on the probability distributions. In other words, no matter how I scale the hazard, I'm going to get a valid hazard out. So I'm going to get a valid probability model out. And I'm going to contrast it with the additive hazards model, the all-in additive hazards model, where because that is additive on the scale of the hazards, well, we have the possibility that we might creep into negative hazard territory. And so we might actually stray outside of the set of probability distributions. Now, there are corresponding advantages, which we'll come on to, for why you might still prefer the all-in model, but it doesn't have this closure property.
A recording.
And finally, kind of at the other end of the extreme from a fixed point, is if starting from here, I can get to almost anywhere. So this is a notion of transitivity, or maybe almost transitivity. If I can start at this distribution and eventually get almost anywhere, well, that means that the model is, in a sense, very flexible near this point. So that's also, again, a feature that we might or might not want in our statistical model. I mentioned that I was going to invite you to think about a notion of comparing distributions. So using these families of transformations to compare distributions, and then to start asking a question about collapsibility. So here's how I'd like to begin. Imagine that if I've started at P and acted by V, and I've ended at P prime, well then in a certain sense we might define the difference between P prime and P. So that sort of O minus is kind of like a generalized difference as V. If it takes V to get me from P to P prime, then the difference is V. So maybe we'd like to define it that way. There is a problem with that definition. It's a nice idea, but sometimes for an arbitrary pair of distributions, there may be no V that gets me from here to there. And so this is, for example, the problem that Kelfish and Prentice addressed when they were thinking of it, again, in the setting of a Cox model. Here's two distributions, well, that their hazard functions aren't proportional. So no amount of proportional hazard scaling is going to get me from one to the other.
A recording.
Here's how in the paper we suggest getting around this problem. Basically, the idea is to say, instead of comparing distributions directly, we're going to compare summaries of distributions. So where we've got the square brackets here, we're sort of imagining taking all the information baked into that distribution and collapsing it down to a much simpler object. For example, a mean. We're still going to have a vector space action on those summaries. So you can see we have a square bracket object there, a summary acted on by a vector.
A recording.
But now that's sort of taking place in a much lower dimensional space. So if we're going to do that, while still making sense of the fact that we have this original group action that takes P, say, scales the hazards to get to P prime, well, we'd like it to be the case that if I summarize first and then act on it by V, or if I act on it by V and then summarize, well, it doesn't matter. It's the same either way around. So if you like a commutative diagram, it looks a little bit like this. We know that for every element V in the vector space, we already know that we have a transformation of distributions. That's the sort of dot V there, the arrow on the left-hand side. And we're suggesting that we should summarize those distributions using these square brackets into some lower dimensional space, the square brackets P there, in which there is also a transformation by the same group, dot V, written the same way. And the point is that it shouldn't matter which way you pass around this diagram. So if you like, what we've got on the left-hand side is the kind of comparison that might exist in a standard parametric model. It insists that within these parametric families, the comparison is one of dot V. And on the right, we have something that is basically a non-parametric comparison. So it could be done on a much wider class of distributions. But the point is that they're being done consistently. So where it's possible to compare them parametrically, you'll get the same answer as if you compared them non-parametrically. So this P minus P is going to refer to this comparison in the non-parametric sense, but that is consistent with the parametric model on the left. If you like, the fundamental definition is the one on the right, though. Okay, so how does that help us with notion? Sorry, this is just to point out that several other people have thought about this problem as well, about how do you sort of bring together parametric comparisons and non-parametric comparisons. There's some other really nice ideas out there as well. We were using this in the context of asking whether a comparison is collapsible, and I'm going to try and illustrate what we mean by that. The question is basically this. I want you to imagine a large population that we can divide into subgroups, and each of these dots on here is going to be one of those subgroups divided by, whatever covariates you'd like. And in each of those subgroups, we run a large randomized trial, and so we can compare what is the outcome risk for those who are not treated and what is the outcome risk among those who are treated. That's what gives them all a point on this lab plot. So the untreated is the horizontal coordinate, and the treated is the vertical coordinate. The question that collapsibility is asking is saying, well, here's all these, if you like, conditional on the subgroup comparisons. How does that comparison relate to, what if we just looked at the whole population comparison? So when we're writing here, P1 bar, so if you like, P1 is the specific subgroup treated risk. P1 bar is the whole population, the average treated risk. P0, the specific populations, untreated risk. P0 bar, the average across the whole population. And we're asking, if we compared those two distributions, how would they relate to these within the subgroup comparisons? So the point here is that there's different ways we could compare them. So here's one. So this is imagining a binary comparison here. I've overlaid, if you like, the contour lines associated with scaling odds or logistic regression. So what you've got is that, again, along that identity line, along the diagonal line there, there's no difference between treated and control risks. And as we move up here, we're seeing that the treated risks are higher. Let's notice something. If you look at the most extreme of the sort of odds ratios that are available in the subgroups, you'll see that the whole population, if you averaged across the whole population, the implied odds ratio comparison there isn't even within that bound of the highest and lowest odds ratio. That should feel surprising initially, right? You sort of go, wait a second, is that really an average? And I guess the reason it's not a surprise is because of the way that means behave with objects. So, for example, if I was to unwisely attempt to fall into a gymnastics bridge here, then my center of mass would not be located in my body, right? It would be somewhere sort of underneath it. Then I would fall over. The other line that I've drawn on here is a dashed line that corresponds to, what if you average the odds ratios of the individual subgroups? And of course, that must lie in that middle range. So we're averaging geometric mean of the odds ratios. So this is what non-collapsibility looks like. The average comparison, P1 bar minus P0 bar, isn't even in the range of the conditional comparisons, P1 minus P0. That's what we're meaning by these angle brackets, kind of like the range of it. That's option one. Option two is this. Imagine now we're making a risk ratio comparison. So these are the contour lines for risk ratio comparisons. Immediately, you're feeling a little happier here, right? The most extreme risk ratios are marked now, and that overall global average, the red point, is kind of in the middle. So if we draw a line through it, we do have that. But you'll see that there's still a sort of slight irregularity, which is that if you average the risk ratios, the geometric means, you don't have the average comparison, sort of the risk ratio associated with the whole population. So we describe this as a weak form of collapsibility when that overall risk ratio does lie within the bounds, but it isn't exactly on. So this, exactly as Anders pointed out immediately, happens when you have straight line contours, then the set is going to be convex, and so that point is going to lie in the middle of it. As soon as you have curvy contours, all bets are off. You can guess where this is going. Here's a risk difference comparison of exactly the same points. So if I overlay the extreme risk differences, again, of course, because they're straight line contours, the average, the overall comparison is going to lie in the middle. But we have this additional feature now that actually the average risk difference is precisely the same as if you averaged across the whole population and looked at the risk difference. And that's really because there's a basic compatibility with the sort of underlying geometry of probabilities here. These contours, you can see they're kind of evenly spaced with respect to the probabilities. So there's a stronger condition when these two means actually coincide. And that's what we call strong collapsibility. Okay, and finally, the fourth possibility is who knows. So there are some weird possible comparisons. This is called the power odds flow. So if you were to raise the odds to a power, these are the comparisons that are possible, but these points are totally inaccessible. So even though in a sense this is a non-parametric comparison, still these points are not reachable. So we just have to say,
a recording
question doesn't make sense. Okay, I'm nearly there, I promise. We're going to talk about how these building blocks that we've described, the flows, these vector space actions, how they're a bit like Lego bricks. This is a comment from one of the referees that we really liked. And I guess the analogy is like this. Lego bricks work so well because there's standardized inputs and outputs. And so you can build whatever you want. So here's our standardized inputs and outputs. Here's our Lego bricks for regression models. Imagine you have some parametric model with, in this case, some number of parameters, V1, V2, V3, and so on. And I mean by a parametric model, okay, if I give you all of those, then you can give me a model P, a distribution P.
A recording.
I want to expand that by one flow. So this is this dot operation here, which is going to give me, given a pair, a distribution, and a vector, it's going to give me a new distribution. Well, you can see that you get an expanded model. This alpha here could be read as append or add or whatever you want. But given a model and a new flow, we can get a new model with one additional parameter indexed by V. And the reason that's really cool is not only can you define the model, you also get derivatives, which is really helpful for likelihood optimization. The details here, of course, matter a great deal, but for these purposes, the details are the two derivatives of the flow are the only things you need to know, along with the existing model's derivative. What that allows you to do is to modularize. So you can say this flow, here's its two derivatives. Okay, now I can use it with any other flow, because that's all I need to know.
A recording.
And then the final thing that puts it all together is just a notion that this is a really cool computer science idea. Given a way to take an existing sort of intermediate result and a new thing and combine them together, that's the alpha. Given a starting point, a model with no parameters, M0, and given a list of flows, we can kind of zip it all up. And no matter how complicated, in one step, you can just write down likelihoods and so on. So in the R package, this is the kind of way that it gets implemented. And I just want to call attention to the fact that the M0 is here. So the starting model is a standard normal. And then you can pass it a list of flows. They get zipped up. Each of them gets a covariate effect associated with it. And hopefully you get something meaningful. Priyan is going to show us some examples of how this works.
A recording. It
has no challenge.
A recording. Okay,
thank you. I'm going to talk very briefly about the applications section of the paper. And to do that, I want to start by introducing another flow into our into our toolbox of flows. And this is another flow of the transformation model variety. And we've called it in the paper the Möbius flow. And here is the way it acts on CDFs, but maybe it's easiest to understand using a plot where we've here I plotted what if you transform a distribution through the Möbius flow, how the median before the transformation maps onto the median after the transformation. We're particularly interested in positive values of y and actually positive values of v. So these blue curves are of interest. And in fact, if you created this plot for any of the quantiles, it would look exactly the same. And so when you're thinking about what it does to a distribution, well, just remember, so what this is squashing down things to the right of the plot and making them tend towards an asymptote of 1 over v. So if you had the quantiles of a distribution, it would be squashing the larger quantiles more than the lower ones. So it's sort of compressing the distribution like this.
A recording.
So bear that in mind, but then also let's see what happens when we compose this Möbius flow with some other flows. And I also want to bring in a covariate, a positive covariate x, which is time or age in some way in most contexts. So let's start with a standard log normal distribution. Then let's apply the Möbius flow with covariate 1 over x. Then let's scale it and translate it. Maybe one way of understanding what's going on here is to see how the median tracks through the different flows. So the median of a standard log normal is 1. If you apply the Möbius transformation to that, you get x over x plus beta 1. And then you scale it, you multiply it by beta 2, and translate it, you add beta 3. And so some of you might recognize this equation as either with or without the beta 3 as looking similar to what's called the Michaelis-Menten model. And with the beta 3, it's the modified Michaelis-Menten growth model. And this has been used in many different settings, as I understand it. So in growth modeling, it's used to model weight or height of infants, let's say, as a function of age, but it's also used in biochemistry to model the concentration of some enzyme in an experiment over time. And so you see it's sort of this kind of shape where you have a starting point beta 3, the beta 2, so beta 3 sort of controls where you start, beta 2 then controls how far above that the asymptote is, and then beta 1 is a sort of half-life parameter, how quickly are you reaching that asymptote. And so when we saw that we could rediscover this model using regression by composition, we thought, well, let's try fitting some data, some Michaelis-Menten, modified Michaelis-Menten. So let's try and fit that model to some growth data. And kindly, Walters et al. Shared some data with us. So they had longitudinal measurements of infant weight from birth to 3 years, and they had in their paper fitted individual modified Michaelis-Menten growth curves to each child using nonlinear least squares. And they did report having some computational problems. So we wondered, could we maybe resolve those using regression by composition? So we're going to compare what they did with this model, which is almost the one I showed on the previous slide, but I have now added another flow here, the power flow, the one that raises the argument of the CDF to a particular power. And this leaves the median, well, to a distribution with median 1, it's going to leave that median unchanged, but it's going to draw in or push out the other quantiles relative to the standard log normal. So we need that, otherwise we would be fitting a model where the dispersion is not in any way estimated from the data. So that's why we add that power flow there. So the two approaches, the NLS that they used in their paper and our regression by composition estimated by maximum likelihood, are both fitting the same median curve, but they do imply a different variance structure. So nonlinear least squares, if you like, is implying a constant importance of deviations across ages, whereas our regression by composition setup here has naturally a variance that is increasing with x. And also it has this implied degenerate distribution at x equals 0. So that's why we have to be a bit careful about our choice of time origin. So at x equals 0, our model is going to place all probability mass at y equals beta 3. So we'd better not interpret x equals 0 as birth, because that would mean no variation. Every baby is born with exactly the same birth weight. And so it seemed better, I'm not saying perfect, to tune the model, if you like, by shifting age to represent roughly time since conception. So that's what we did. And this is just showing a selection. I think there were 97 babies or something in the entire data set. And here is just a selection of 10 of them, where the red curves are showing the NLS fits, and then the blue curves are showing the regression by composition fits on top of those. So you do see that in many of the cases, they are very, very similar, which is perhaps what we would expect because we're fitting models that are very similar. But we do see in some places a slight difference. So with this child, for example, and what you see makes sense, that the red line, which is the nonlinear least squares, does track that high weight at the end rather more than the regression by composition fit does, because regression by composition is already allowing for the fact that variability is going to increase with age. So it's not as concerned, if you like, about that large point at the end and fitting that point as closely. I'm not going to have time to talk about this example, but this is another example in the paper, and I just wanted to draw very quick attention to this example, in the sense that this is somewhere where we use regression by composition to form growth charts. And I think what we've just discussed about the variance structure being that is implied by regression by composition here, and the way in which it is amenable to parsimonious covariate modeling, if you like, might have applications when you want to create growth charts, maybe for children with a rare disease where there aren't lots of data available in order to do it in a very flexible way. And this sort of semi-flexible way might give you some nice compromise between what is available at the moment. And then finally, I want to talk about this final example in the paper, which is one with a binary outcome. So this is a randomized controlled double-blind trial of combination antiretroviral therapy versus monotherapy in individuals with HIV. And we focus on the subset of the data that are freely available in this SPEF2 trial package in R. The outcome for this analysis, at least, is disease progression or death within 2 years. And the observed event rates are twice on monotherapy what they are on multi-therapy. Even in the original publication, there were concerns about generalizability to other HIV-positive populations, there are many baseline covariates available in the data set, including the key one of CD4 cell count. And so we go into this in quite a lot of detail in the paper. There is no time to go through this now, but there are reasons to believe that the possible treatment effect, that there might be a possible treatment effect reversal at low risks and the leveling off at high risks. In other words, the Labe plot plausibly might look something a little bit like this. And I say guided by earlier principles. We sort of have a first principles type attempt of an argument of why it might look like this in the paper. But of course, it's not really first principles, so earlier principles.
Recording.
What we were thinking about in this analysis was, well, this Labe plot does not belong to the contours of any of the standard GLM models that you get with the standard GLM link functions. Can we compose some familiar blocks together to create something that might allow us to estimate something like this if the data indeed imply that this kind of relationship is there? So how did we do that? Well, we started with standard logistic regression for the baseline covariates. That's why I have the scale odds there. But then we added exactly as Daniel was showing earlier, the two kinds of scale risks. So I think in the demo, he called it the unhinged model. So we want to unhinge at the origin so that we do give the model the chance to decide that there is this reversal of treatment effect direction at low risks. So that's why we add both of those flows. But then we don't want only to be able to estimate straight lines, because we do think that there's probably a curved relationship. So we add treatment as well into the scale odds flow with the covariates. And then we're going to add this strange power odds, the one that Daniel put up when he was talking about collapsibility, this strange thing that allows for S-shaped Labe plots. If we compose that with the other ones, we would never want to look at it on its own, this power odds. But if we add it to the composition with the others, it allows maybe both a convex and a concave curvature, or this leveling off that we think might be going on, to be estimated at the end. So when we do fit this model, this is the Labe plot that we end up obtaining from the parameter fits, the maximum likelihood fits of the parameters. So it does look a little bit like the one that we posited from earlier principles. And I will now give you the confidence interval around that. And you see that it does get extremely wide to the right-hand side of the plot. And I've added on the horizontal axis here are the fitted risks under monotherapy from the logistic regression model. And we see that the data, if you like, are at the low risk end. And so it's not surprising that we don't really have much of an idea what's going on up here where we don't have any data. And there's this nice feature in a way that we would be, we would get a p-value of less than 0.05 only for this interval in the middle where the data are, and there isn't strong evidence of a treatment effect beyond there. But we do have this feature that, albeit not really significant, but there is this crossing of the identity line at the bottom here. And maybe we contrast that with the Labe plot from logistic regression, which actually isn't that different where the data are, but is very different where there aren't any data. And specifically, we can draw your attention to the fixed point of logistic regression at either corner, and specifically the one at 1, 1. So that's where logistic regression, simply because of the choice of model, is very sure what is going on there, whereas our unhinged model is not, is more honest, if you like, about our lack of knowledge of what is going on away from the data. So that is all I'm going to say about the applications, and I'm now going to hand over to Mats for some discussion.
Thank you
very much, Rian, and thank you, Daniel, for starting this off. The last part of the talk, I will take a step back, summarize the points briefly that Rian and Daniel made, and also talk about a bit of a bigger context and reveal some limitations. So first, what have we done? We have described a way of doing regression by composing transformations of distributions. And we have argued that many well-known regression models fits in this framework, in the sense that we can describe them or reformulate them and as this type of transformations. The inference results we have, which we haven't described in broad detail, except by giving you illustrative examples, are highly parametric. Vanilla maximum likelihood, if you like. So when is this useful? I would argue that if you have a good reason, and this might be seen as this conventional or historical British style of doing statistical modeling, if you believe that you have a strong reason to believe in the particular parameterizations, like experts claim they have when they use, say, a Michaelis-Menten model, or go to a biochemist that might have a Hill model for their pharmaceutical compound and so forth. Then you might move on, strongly believe in your model, and fit this, and then borrow strength and gain power because it's highly parametric. It relies on a lot of assumptions. What do you do if you don't have such a justification? So now there's a big wave of non-parametric and semi-parametric work, and you might ask, how does this work fit with that popular literature right now? And in some way, it sits uncomfortably, in the sense that we require these models to be correctly specified. The inference results we have so far, they rely strongly on these models being correctly specified. If you're worried about them being misspecified, maybe this is not the way you want to go. Maybe you want to do something different. So when I say maybe you want to do something different, I mean in terms of using our literal inference results. By writing the models by transformations in this particular way, that doesn't prohibit you from thinking about these transformations being more flexible. For example, we can think about extending and allowing the index spaces to be function spaces and just simple parameter spaces. The final thing I want to briefly mention is the relation to the machine learning literature, in particular here normalizing flows, which is often a way of describing neural network, and also generative models, which often are, by the way, fitted by neural network anyway. What's the relation here? Because Daniel mentioned these Lego bricks, the way of thinking about these transformations as being Lego bricks that we can do step by step. But that's precisely how people think about neural networks. They take their data points, they make a transformation that's invertible, and diffeomorphism, and so forth, and they do that for each layers. So what is the relation? Well, they are closely related. One superficial way of saying it is that we are transforming distributions. We committed to having a P0 distribution that we transform in every step, versus the machine learning sometimes say that they transform data points. So if you're looking at the so-called transformation models from the statistical literature, that's exactly the same exercise. There is no difference. But you might think about certain transformations as harder to express, at least at transformational data points. And the other difference is that we are highly parametric, of course. So we are in a very restricted class. And what we gain from that is that we can describe certain features such as collapsibility, and we can also make this simple likelihood-based inference. And again, if that's not what you want, then you might go to a more flexible class, and you might benefit from that. So I will end there and let the discussion take over. Thank you very much.
So as per tradition, we now move on to the invited proposer and seconder of the vote of thanks. So first of all, I'd like to call on Steve van Steelant, University of Ghent, to propose the vote of thanks.
Okay, well, thank you very much, and a big congratulations to the authors. Empirical practice, as we all know, is very much dominated by simple main effect models, and this paper proposes something more ambitious, a compositional grammar that builds complex models from simple pieces. that are interpretable, and I'm not the reviewer of the paper who made the connection. But this is what I came up with, and actually I'll get back to this because I think the connection with Lego blocks isn't perfect. Let me go back to the example that Daniel went through, starting from logistic regression to model the effect of age on a binary outcome. We can subsequently model the effect of treatment by scaling the risk of outcome being 0 by a multiplicative factor. And we can even go beyond this. We can also, starting from this model, scale the risk of outcome being 1, again by a multiplicative factor. And that gives us quite a complex structure already to work with. That structure depends on how we order the flows. Here I switch the blue and red flow, and that gives us a different model. So what is the role of the framework? I'll give 2 perspectives on this. The most obvious is that the aim of the paper is to provide flexible modeling, and to some extent, I think that is the case because we can build quite sophisticated models with just a handful of simple pieces, and I think this is very much worth exploring, partly in connection to machine learning methods that often lack structure, where explainability often comes as an afterthought, where inference is lacking, and there's maybe some hope that the parametric structure gives us an opportunity to do better here. But on the other hand, there's many choices that must be made with this framework. There's many different flows that we can work with. We can play with the number of flows that we consider. The ordering of the flows matters. And in each of the flows, there is linear predictors where, again, we can make different choices. And I think some input is needed on how we should navigate those many possibilities that we have. And in practice, to provide flexibility, some form of regularization will be needed at some point. I think this remains to be developed, but I think is worthy of consideration. The downside is all of this is then also going to complicate inference. But again, I think this is worthy of further exploration. But I think what is closer to the aim of the paper is parsimonious modeling, at least as I have understood it. And reflecting on my own field, causal inference, I think methods development has very much gone to either one extreme or the other. There's a lot of focus on scalar estimates, like the average treatment effect, which is very useful. And on the other extreme, there's a lot of focus on non-parametric functions, like conditional average treatment effects connected to causal forests, for instance. One extreme has a bit the drawback that there's only so much we can get out of a single number, and that may mean that we oversimplify the questions that we can actually address and the answers that we can provide. At the other extreme, there's a risk of losing insight if we come with sophisticated non-parametric methods. Inference becomes more complicated, and there's very little in between within causal inference developments. And in that sense, I very much welcome the paper's perspective to give another role to semi-parametric thinking or parametric thinking. But the big question is, does regression by composition really attain parsimony? And I'll give 4 critiques related to that question. The first is that there is a danger in building models of such complexity that it defeats the very purpose of parsimonious modeling. And let me go back to the model we've been looking at here that gives a very simple relative risk interpretation in terms of the risk of outcome being 0. But as soon as we add one flow to the model, that same relative risk becomes horribly complicated. And so that feels a little bit as if we start from a very simple structure that we have carefully built. But once we add one component, it completely messes up everything. And it might make the model better. It's just the point I want to make is that it can suddenly give us a very different structure than we may have thought before. And so the elegant use of group theoretic structure based on simple flows that is very well worked out in the paper, in that sense, doesn't really translate necessarily into a simple modeling exercise where you can build a model sequentially from the ground up, adding complexity as we go. In that sense, relating to the group theory, I think the abelian case, as I guess it would be called in group theory, where you could interchange flows without affecting the end result, I think would feel like more scientifically interpretable, at least easier for practitioners to navigate. But probably this would then be too restrictive. In any case, I feel like this point could use a bit more scrutiny and guidance for practitioners. As we saw on the previous slide, the parameters don't necessarily have a simple interpretation as we keep on adding flows. And that made me wonder a little bit, why do we really want to parameterize or have flows, say, related to the relative risk of death and survival in one and the same model when it's really messing up interpretation so much? And the reason why I raise this question is a bit linked to the next point. So consider the model here where we have two flows. Oops, not sure what I did. Okay, so the model here is the one we looked at before, except age is left out here. Well, this is a model that cannot be identified, basically because we have two treatment effect coefficients and only a binary treatment. This is carefully recognized by the authors. If we go to the model here that now includes the age effect, well, this is a model that can be identified, but the observation I just made is indicating that information about the two treatment effect coefficients doesn't really come purely from the data, but it also comes from the fact that now we have a parameterization of the age effect, which is linear on the odd scale or the log-odd scale. And that I think is worrying. It's signaling a form of lack of non-parametric identifiability that for me would ask for a more constrained form of modularity. There's a bit of a danger that the two parameters called gamma 0 and gamma 1 in the model that index the treatment effect, it's tempting to believe that they capture treatment effects, but actually they might also carry information about the age effect. And I worry that this may lead to misinterpretation or misuse. Collapsibility is a big theme in the paper, and I think the authors make some beautiful points there related to what structures provide collapsibility. There's a lot of emphasis on models designed to deliver collapsible effects, and I believe collapsibility is really important if we wish to interpret, or let's say report effects on a certain scale. It's important to be aware of non-collapsibility. But because of that difficulty in parameter interpretation, the authors report the effects in terms of Labby plots, which I very much like. But I believe these plots are well interpretable no matter the scale that you work on. And because we can just see the risk on the x-axis on one treatment arm, the risk on the other treatment on the y-axis. I wonder, why do we need a collapsible parameterization if this is how we are going to report the results? Why do we want to prioritize it? Collapsibility is a fragile property. We lose it when there is effect modification, when there's model misspecification. I believe it is a secondary concern to correct modeling. And finally, Mats made this point as well. So the authors position the framework as encoding scientifically grounded structure, but scientific knowledge rarely dictates specific flow sequences, not the least in view of the complexity of the framework. Imagine that I had some scientific knowledge about one flow. There's still the complexity. Where in the chain shall we put that information? In practice, at best, we will have some partial mechanistic insights. What goes wrong in one flow could infect the other flows. And because of that, I believe that parsimonious modeling and estimation should concentrate more on either what we know or what we are primarily interested in. And this links a bit to the work that we are developing. And I'll just say briefly a few words on assumption lean regression, linked to an earlier discussion paper that has evolved quite a bit since. And I'll give a bit of a very quick idea so you can see how it links to the proposal here. So let's keep three key principles in the framework. The first is we parameterize only what we care about, which is the effect of a treatment A here on an outcome. And we do that directly linked to the Labby plot on the right. Okay, so the Labby plot on the right, along with the model, gives us a way of mapping the risk mu0 in the absence of treatment, say, onto the risk mu1 in the presence of treatment. Theta here is kept simple as a constant, but it can also be a function of x, if you like. Then next, we work with a risk function that purely encodes errors in the causal effect. In fact, the errors that we make in the Labby plots, because we quantify how different mu1 is from what is predicted under the model. And in order to make that coding independent, in the second term, we do the reverse situations, flipping the coding of treatment. But this risk function is exactly encoding the errors that we make, possibly due to model misspecification when we make this Labby plot. And so we can define theta as the minimizer so that we minimize the errors in that picture. And then the way how we do it, well, to do this, we need to learn mu0 and mu1. We can use flexible methods. We could use the methods that the authors developed. We can use machine learning. And to ensure that we can come up with valid inference, debiased loss minimization is used. Let me conclude here. I believe the authors have brought us an ambitious and mathematically elegant framework with a very rich and useful vocabulary. But what is missing is syntax rules with guidance. And I believe there's a need for more constrained modularity so that we can work with non-parametrically identifiable models that are also physically plausible, like have some guarantee of giving predictions between 0 and 1 when the outcome is binary. There's some very nice work by Linbo Wang and Thomas Richards and Jamie Robbins linked to that. For practitioners, I believe it is hard to navigate the fact that the ordering of the flows matters, and the fact that as you add one flow, you may lose your structure that you have built. Personally, I find for these reasons that expressing models in terms of this Unix syntax, if you like, that it obscures the complexity of the models that we work with. Nonetheless, this is very much a warm invitation to the authors to further strengthen the project, and I'm very happy to propose a vote of thanks to the authors for a very timely and thought-provoking paper. Congratulations.
I'd now like to call on Peter McCulloch, University of Chicago, to second the vote of thanks.
Tell me which button not to press. Well, I want to begin by commending the authors for addressing a topic very dear to my heart. For many years, the consistent specification of statistical models for scientific investigations. And I'll just begin by saying in one part, in the literature today, there are two what I would call contradictory notions of individual treatment effect that are prevalent. In one area of the literature, it's defined as a contrast of counterfactual outcomes. In this paper, the other one is the notion promoted in this paper that the individual treatment effect is a contrast of unit-specific probability distributions, one given the treatment and the other given the control. These seem to me to be entirely contradictory things. And from my point of view, the second one is correct and the first one is nonsense. So I could easily fill my entire time with glowing remarks about these sorts of things, about commutative diagrams and flows and treatment effects. But fate casts me in the role of seconder of the votive fact, with an obligation to fulfill the role that, at least in the past, was expected of the seconder of the vote of thanks. Fortunately for me, the authors have been extraordinarily generous in providing material for praise and material for criticism in more or less equal measure. So I will, these remarks will focus without sentimentality on the shortcomings, leaving the positives to other discussions. First shortcoming, in my view, is that Several of the examples focus on applications involving growth curves and such things, applications where one might reasonably expect non-trivial correlations among observations. For example, a plant whose height is above average after 5 weeks is more likely than not also to be above average height after 6 weeks, 7 weeks, or 8 weeks. And yet, so far as I can tell, none of the flows that are mentioned in this paper are effective or capable of generating correlations from an initial distribution, a starting distribution, which in every case in this paper has independent and identically distributed components. So the first shortcoming is what I would call undue and unhealthy emphasis on models having independent components, particularly in a culture that you find in certain application areas, such as non-parametrics, which is such that independence doesn't even count as an assumption. That seems to me a dreadful mistake. And I just point out to you that that's not the norm in all areas. It's certainly not the norm in applications to field trials, for example. It's not the norm in applications in genetics, in applications in spatial work, in lots of areas. But in biostatistics, it somehow, everybody assumes it. We didn't hear a word independence today, just as an example. So what I want to do is to begin by saying that this is totally unnecessary. This assumption on independence is totally unnecessary, and I want to go about saying how you might possibly get around it. So my comments here are split into two parts. The technical part, which I will go through fairly as quickly as I can, and the non-technical part. And hopefully I can manage that. Okay, so the authors will have seen this before because it was certainly mentioned in referees' reports, but it was totally ignored. And it's the importance of consistency. Now, getting consistency right is trivial if you have independent observations. It's not trivial in applications where you do not have independent components. The only thing that's stated in the paper is that we begin with a bivariate process, x, y, and we take from that the conditional distribution, as if those are going to be consistent, mutually consistent, sampling consistent. It is true that if you start off with a bivariate process, it is a process, and therefore the finite dimensional distributions are, by definition, mutually consistent with one another. But that finite consistency of the finite dimensional bivariate distributions does not imply consistency of the finite dimensional conditional distributions. So just taking your conditional distributions from a process, an arbitrary process, does not guarantee consistency. The conditional, what does consistency mean? It's got to do with sampling. You want to say something about the process from observations on the sample. In the sample, you get to observe the x's and the y's with the usual interpretation. And this conditional independence assumption in the middle of that says that the response distribution on the sample, conditional on the entire x process, depends only on the x values in the sample. That is consistent, and there's no guarantee that in the literature on experimental design, where x is typically a treatment effect, this is also called lack of interference. Again, that's something that I would have expected to see in this paper, but no. So if you want to try to take this a little step further, you have to begin by talking. So all probability distributions that I'm talking about now are not probability distributions on the real line. They are probability distributions on Rn, and it's on that object that things act, and it's not necessarily component-wise. So a regression model, a regression process, I should say, in this setting is a consistent family of these conditional distributions. The second thing that you need, and I'm not going to say much about flows, or except very little, but you do need this thing. You need to be able to compare the distribution under treatment with the distribution under control. And you want to, if you're going to be using flows to do it, you better have those on the same orbit or some connection between. So there has to be an automorphism group associated with every factor, every covariate. And in the case of treatment, the automorphism group is just two elements in it. It's the identity, and it's the one that switches around control and treatment. In other circumstances, the automorphism group could be quite different. Could be this whole symmetric group, and there's multiple levels. And so we say that two configurations, the configuration means the design, if you like, the covariate configuration for the entire sample, are automorphically equivalent if, when you make this switch component by component, x prime is just sigma x. This is not, the permutations that I'm talking about now are permutations of treatment levels, not permutations of the observational components. And we say that the model is automorphically equivariant if, when you do that, there is an adjoint transformation takes place on the parameter space that makes the two probabilities equal. We're all familiar with that. You know, if you fit a regression model, a factorial model, and you change the labels on the treatment, well, the parameters will come out in a different form. So that's exactly what this adjoint transformation is. And what it does is it establishes a relationship between exactly the two distributions that the authors want to compare via their O- operator, which I will come to in a moment. And so this guarantees that they will be in the same orbit. Right. Okay, so now how do you measure treatment effect? Actually, it's much simpler than was described here. You have a response Y, a covariate X, and a treatment. And you have some sampling consistent family of distributions. And so in the way that I'm going to describe it, the treatment is just a function on the parameter space that has a certain property. First of all, the null treatment axiom is that there's some parameter point that satisfies this conditional independence assumption. And the zero treatment effect is going to be exactly associated with this conditional independence assumption. I was a little surprised that I did not hear conditional independence in the paper. This is asymmetric in the treatment and the covariates. And it's not a tautology, or it's not a consequence of flows. And it's natural only in conjunction with, well, natural, and I'm using the word natural in the natural sense, but also in the group theoretical sense of commutativity here. So the function is commutative with respect to the automorphism group that acts on treatment. Okay. So I haven't talked about flows yet, except you'd say that it's, you know, it's okay. I'm not arguing against it. But sampling consistency is absolutely the top one. If you don't have sampling consistency, you might as well go home. You don't have anything. You can't say anything about extra sample units whatsoever. And if you don't have that, you don't have anything. Okay, so the equivariance group, these are matrix groups. It's not related to flows. This is typically a non-commutative group. And it'll be a discrete group quite frequently. So it's not associated with flows necessarily. Well, it can be associated with flows. So the null treatment set that I'm talking about is set there. And the treatment effect is just a Well, in the vector space, in the sort of situation that the authors are talking about, it's technically just a homomorphism of group representations in which this set theta naught is the kernel of the homomorphism. If that doesn't mean anything to you, you can ignore it. But I will point out that 91 years ago to the day, a paper was presented to this society in which exactly these issues came up. It was presented by Jerzy Neyman, and Ronald Fisher was in my shoes, or maybe I'm in Ronald Fisher's shoes, whichever way around it is. And if you haven't read the discussion of that paper, you should read it. And this issue comes up as to what the meaning of treatment effect is. And so Neyman had a notion of it, what was called average. Somebody used the term average treatment effect. That was what Neyman was using. That's when it was presented 91 years ago. Say, and if you're wondering, the answer is no. I was not present at that meeting. So what I want to discuss now is whether the O- operation satisfies a null treatment assumption. Okay, let's move on. So I've written now here the null treatment assumption is associated with conditional independence. What is the O- assumption? Well, I read that paragraph many times and tried to figure out what it means. It says this is you're allowed to press the...
Yeah, left and right is good.
Okay. Okay. So we're talking about, so think of t being 0 here and sigma t being 1. So this is the probability conditional on x of anything under theta, and the one and t is 1 here, sigma t is 1 and t is 0. Well, you can take the sigma out and put it in front of the theta, and it's the adjoint transformation. And so the thing on the right is the two distributions, and they both have the same x and t, so they're automatically in the same orbit, and that's just sigma prime theta minus theta. So the O- effect is exactly associated with this adjoint transformation associated with the automorphism group associated with treatments. Now, so this is the null treatment effect. It's the set of all parameter values such that for all of the automorphism group associated with treatment, it doesn't change the parameter. In algebraic terms, that is the trivial subrepresentation if we're talking about linear representations. And the fact of the matter is, and it's an astonishing fact, that for every example in the paper, these two sets are the same. Now, you should be amazed at that, because one of these is a statement that's probabilistic, and the other is a purely algebraic statement. There's absolutely no reason why these should be the same. So I'm going to leave it to the authors in the reply to tell us which sort of amazing coincidence or amazing thing this is. Is it purely a coincidence that these two sets are always the same, or at least for all of the flows in the paper, or is it simply an oversight? Or, well, I think I've said enough. Okay, so that's the technical part. I want to move on to the non-technical part. Apart from group action, which I thoroughly approve of, the paper has a couple of subsidiary themes, neither of which meets with a similar degree of approval from me. One of these is Neyman-style averaging for treatment effects, and another is random sampling. It's not that I object to random sampling, but both themes are peripheral to the topic of the paper, and the paper would be much improved if both topics were obliterated. But given that they are used as motivation, they are fair game. The phrase randomly selected observational unit with script F representing covariate information is actually taken from an earlier version of the paper, but it explains the notion that persists in the final version. But it's helpful in explaining why the authors insist on regarding the covariates as random variables, which would not be my choice. Now, so I want to say a little bit about random sampling in scientific work. I have worked for 30 years as a statistical consultant in scientific work around the university. And not once in that time has the issue of random sampling ever come up. I'm talking about random sampling, I'm not talking about randomization, which is a totally different thing. Certainly, random sampling does occur for legally mandated, typically non-comparative purposes in accounting, auditing, and for administrative purposes in survey research, such as the determination of unemployment rates or infestation rates in ecology. Absolutely. But random sampling in a laboratory context or in agricultural research is a totally different matter. It conveys a certain image of an errant scientist wandering the lanes and byways of Hereford or Hertfordshire in search of plots, informing the occasional bemused landowner that a certain plot in the middle of one horse pasture has been selected randomly by satellite imaging to partake in next year's sugar beet trial. Surely that must be regarded as implausibly eccentric, even by English standards. None of the authors are English, so I hope I can get away with that. To be fair, I hasten to add that, at least in my time, fairness was not a traditional obligation for the role of seconder. I want to conclude by addressing two questions. First question is, if there is no random sampling, which there is never, almost never in scientific work, what is the basis for inference? Well, the answer to that paper, the answer to that question is present in tonight's paper if they had assumed consistency, which I'm sure they have taken it for granted, but they haven't explicitly assumed it. So a regression model with consistency is the basis for inference. A regression model not only specifies the joint distribution for the units that occur in the sample, it also tells you what the joint distribution is for the units that are not in the sample. Those are the ones that you're interested in talking about. Typically, there will be infinitely many of them, and you might not necessarily talking about individual values for other, but averages over the infinite population. And that's the basis for inference. Now, of course, the model, of course, may be deficient. That's always provisional. Model is always provisional. It may be deficient on various grounds. The design may be deficient. And so that means that the inferences will not necessarily be correct. But it's the only thing, it's the only game in town. The second question that comes to mind is if random selection is to be taken seriously, what sorts of selection schemes are permitted? Well, if you look carefully at the paper, you will find that the only selection schemes that are permitted are neutral schemes. That means that the sample as a random subset must be independent of the response given the covariates. That rules out certain sorts of sampling schemes that do occur, for example, in auditing, where people use monetary unit sampling or size biased sampling, those sorts of samples. That sort of sampling is not good. So what does that mean then? If the only sampling schemes that are permitted are neutral, that means that you can ignore the sampling scheme. Well, isn't that convenient? And for the most part, the authors do, in fact, ignore the sampling scheme and proceed with the model, at least as I read the paper. I say that not by way of criticism at all, but by way of commendation. For my part, I am happy to endorse the practice of ignoring all non-existent random sampling schemes. And for that reason, I have great pleasure in seconding the vote of thanks.
Thank you to all our presenters, invited presenters today, for their excellent and insightful talks. As per tradition, I'm going to ask once more for we can show our appreciation by applauding everyone who's spoken. So we now move on to the open discussion. I'll proceed with that quickly by immediately inviting those who are inviting those who have given their names already. So first, I'd like to call on Stephen Sen, consultant statistician at Edinburgh.
So this is an interesting, innovative and challenging paper, and I want to pick up something in the abstract. It refers to a mechanistically motivated binary regression model. And I want to say straight to start with, I'm all in favor of mechanistic motivation, but I have my doubts about binary regression. So let me explain to you how clinical trials work. I've been involved in a great number working in the pharmaceutical industry, and of course you start with a treatment and you then take a measurement, and you might think that the next thing that happens is you get some clever statistical analysis and then you get some conclusions. In fact, in between, unfortunately covered by the particular thing here, is you get an information destroying transformation. I can assure you, as a statistician working on such projects, these are almost impossible to avoid. I give you a very, very large set of them if you're interested, but there isn't time here for me to discuss them all. So, trying to advance. The mouse, click up. Oh, there we go. So, the pointless collapsibility debate, in my opinion. We worry about what we should do with binary data, but in fact, almost no data are binary. You might think they're very common, but in my experience, they're not. They nearly always involve some sort of dichotomization, either in space or in time. A medical statistician is someone who classifies mankind into dead and not yet dead. In the long run, we're all dead, and the difference is really how long we are alive. So worrying about the scale in which we should analyze dichotomized data, in my opinion, is pointless. It's a really sterile, arid debate. I don't care. You shouldn't be doing it in the first place. You should use the original scale. You should prefer the left-hand diagram there, the left-hand plot, to the one on the right-hand side, which is the reduction of the information about how long individuals survived into a binary classification. And you might like to think, as an exercise, if you can actually think of some genuine medical data that are binary originally and not by dichotomization. So in fact, creating a dichotomy is a data crime. And I don't necessarily blame the authors here, because obviously they're quite capable and they could have shown us their methods applied to the original survival data in this particular example. And instead, they wisely spared us all of the complications of doing that and gave us the simpler binary data. But that then raises the question, why did they have to give us a dichotomized data set? And I suspect it's simply because they couldn't find a binary one. They would not be able to find one which was truly binary in the first place. There are very few clinical trials of that sort, possibly trials in which cures of infections, for example, fungal infections, are involved. So this sort of thing goes on all the time. And Eric van Swat, Frank Howell and I have recently published a paper in which we try to cost how much what this actually costs the pharmaceutical industry and all the rest of us. And the answer is billions of dollars per year, simply because we take continuous data and we dichotomize them. So the question is not whether we should count the living or the dead, but when we should count them. And the answer is, as often as possible, not once at 2 years. And if you really want to understand the arbitrary nature, then do what I also did, was I simply repeated the binary analysis at every possible dichotomization from 3 months right through to 4 years to see what sort of answers I would get. And you can see how unstable the whole thing is. So I welcome the author's motivation of mechanistic regression models, but my advice is to apply this thinking as far upstream as possible. If you want to get mechanistic, get involved with the original measurement process, not with the stuff which has been destroyed by others on the way. One minor point I'd like to make before finishing, as regards the growth model, I think the particular model used is what's also referred to in pharmacometrics as an Emacs model. And the power version of it is called the Hill model. And in fact, Hill's original motivation in 1910 in developing that particular model was mechanistic. Thank you.
I'd now like to call on Heather Batty, Imperial College London.
Thank you. So perhaps disappointingly, I'm going to just give some very gentle points for reflection. Right, so I think it's worth briefly comparing the paper under discussion to McCullough's formalization of the foundations of modeling. I hope I'm not misrepresenting him. Read the original papers, don't trust me. But treatment has an effect on the probability distribution of the outcome. This is formalized as a transformation induced by the action of a group on a set of baseline distributions. And in the simplest models, the group acts on the baseline parameter space gamma. In regression context, the gamma depends on the observation index via these baseline covariates. Popular choices would be the linear model and the log linear model, depending on the context. Oops. So the regression by composition is an extension of this, in which, at least in principle, all variables are treated, or sorry, effects of all the variables are treated as group elements, with a possibly different group action for each effect. Okay, so others have made this point that an ordering is inherent. This is natural for successive treatment or exposure variables or intermediate outcomes, but it's unnatural for intrinsic variables that are treated at, fixed at baseline. And all the examples we saw, I think, were treating the baseline variables symmetrically, but in general, that needn't be the case. So first question, what is the author's advice? And does that advice change depending on what the objective is? Equivalence classes of models. Okay, so there are two contexts. The one I mentioned, intrinsic variables treated symmetrically, and the other effects are modeled by regression by composition. Or on the other hand, you don't consider this inherent ordering, or you don't interpret it literally. So there might be equivalence classes of models that generate the same distribution over y given x. And the reason this is relevant is that if you are in one of those equivalence classes, then you're not going to be able to distinguish one model from the other on the basis of the data you've observed. Slight extension of that. So the first point, that would be true of any sample size. The second point, there may be models that are statistically indistinguishable at a given sample size and given significance level. So how is model adequacy to be assessed? So the rest of my discussion relates to collapsibility. It's just more general points, not specifically about regression by composition. So most collapsible models, as others have said, are not physical. So for instance, they may lead to probabilities that are not constrained to 0, 1. If you enforce the physical constraints in the fitting procedure, then that makes the parameter space depend on the sample that you've observed. So this undermines the stable interpretation of parameters. So the stability is preserved if you allow fitted values to fall out of range. So I'm thinking here about a linear improbability model, which the simplest. So that would be acknowledging that the model's a poor approximation for some individuals. And that's not permissible with maximum likelihood fitting. So question whether what the implications are for regression by composition, and how comfortable are we with these non-physical models, which don't obey these axioms. As I said, simplest example of a collapsible model for binary data, a linear improbability model. The regression coefficient beta j, if you interpret it purely mathematically, it would be this. Expected change in the proportion of m individuals likely to experience the positive outcome in response to a hypothetical replacement of m individuals who differ by 1 unit in the jth component and are otherwise identical, and m is arbitrary. So at least if I'm thinking about this properly, the interpretation shifts from individual level to population level. So variables that were intrinsic at the population level are not so when treated as population averages. So discuss. And this is an incidental point that the linear improbability model is I think and it's physically implausible, but I think it's the only one that gives you agreement with this Neyman-Rubin treatment effect under the relevant fictitious idealization. I won't go into exactly what I mean here. Okay, and why do we care about collapsibility? Or do we care about collapsibility? If all covariates that are thought to be relevant are measured, should they not be included? I think a case for deliberately omitting them would be that there were too many of them, and that would point back to model assessment. And then a final comment. If covariates are unmeasured, then this is one example where you can still get reliable inference for your treatment parameter in spite of not knowing what those covariates are. So example due to Cox, 1958, binary matched pairs, logistic model, which is not collapsible. And we've absorbed these unmeasured covariates in this all-encompassing nuisance parameter gamma I. So same gamma I that I presented on the first slide. This nuisance parameter for the ith pair captures the unmeasured aspects. And this is the usual formulation in the logistic parameterization. So the treatment effect is beta. If we look at direct estimation of everything by maximum likelihood, then we're going to get the wrong answer. If we look at the collapse analysis, we'll get the wrong answer. But by thoughtful analysis, you can eliminate the nuisance parameters gamma, and you'll get the consistent estimator of beta. Okay, that's it. Thank you, and congratulations.
And now I'd like to call on Vern Farewell from the University of Cambridge.
Well, first of all, I'd like to commend the authors on this innovative paper, which significantly expands the regression toolkit, but as many of you have just figured out, I have to do that by also declaring a conflict of interest in so doing. So in any event, good. What I'd like to reflect upon briefly is the author's characterization of regression by composition as comparing distributions. Their comment that multiple flows are needed to do this, And there a comment in the discussion that the Behrens-Fisher problem is an apparently simple example where this is needed. Now, I also want to note that David Cox mentioned many times that the primary features of a model are should be linked to the research questions of interest. In addition, there are going to be secondary features that primarily influence the method of estimation. So the Behrens-Fisher problem is usually characterized in this way, that you have a comparison of means, which is primary, and the variances are secondary or so-called nuisance parameters. So I'm going to just look at the simple example, which I've looked at previously with David Sprott, comparing log failure times for plastic gears at 2 temperatures. I have 8 observations at the lower temperature, 4 at the higher, defining a binary covariate temperature, which is 0 at the lower temperature and 1 at the higher. Then you can write down a possible regression by composition model, as has been seen many times today already, where we start with the N01, we apply a scale flow and then a translate flow, and in the Behrens-Fisher problem, notably, the temperature variable is in both flows. In the scale coefficient, it represents the log ratio of the standard deviations. In the translate coefficient, it represents the mean log difference. Just to note, this could be formulated directly as a log normal model, but it's better this way for the purposes that I want to make of it. And also, we can also approach some analysis of this using exact methods, but again, to mimic what you might do with RBC models, I'm not going to do that. Now, in the RBC package, there is no defined program to produce profile likelihoods, but there is a log-like function which can be used with bespoke code to produce profile likelihoods. And if we look at the profile likelihood for the standard deviation ratio, you can see here, looking at the axis below, that there's no evidence against that ratio being 1. But rather than proceeding with this assumption, because of the wide range of plausible values from 0.5 to 3, let's do something different. And if we, first of all, okay, let's fit the full RBC model where we have that scale ratio in, we can get a 10% profile likelihood for delta, minus 0.54 to minus 0.10, evidence against a mean of 0. But what happens if we do something different? Let's assume that regard rho is fixed at a variety of values. And got 3 values here, 0.3, 1.10, 2.5, 1.10 being the MLE. And this gives you then what happens there. You can see the profile likelihoods plotted on this figure. And for the values of 0.3 and 1.1, and indeed as for the maximum likelihood profile, all these values rule out, it's not actually visible at the bottom of that, but 0 is here. No, sorry, 0 is here. So it rules out 0, but the one at 2.5 does not. And I put this up because I want to sort of address the question, is that, you know, to what extent is just focusing on delta represent the goal of adequately summarizing the difference between these two groups? And certainly doesn't fulfill the case of comparing distributions. Just in concluding remarks then, I would say, I want to ask the question, is the inference regarding delta indeed the primary question here, that may be problematic, and that it seems clear that the scale flow needs further, closer examination. And the sort of, if you like, a warning here that in the complexity of these regression by composition models, be careful about focusing on parameters in one flow if the distributional comparison is indeed the goal of the exercise. What is thought to be secondary may not be secondary. And finally, just to point out that it seems to me that profile likelihoods are very useful to examine the robustness of conclusions to various model features. And I would take the liberty of encouraging the authors to perhaps make that even easier for the users by incorporating some functions for this in their package. Thank you very much.
I'd now like to call Linbo Wang, University of Toronto.
Hello. So I would like to first start by congratulating the authors for this very interesting work. And that's all the nice thing I'm going to say. And now, there are some discussion points. First is about the philosophy of modeling here, right? So should we really? I think the big question that we want to ask here is when we do regression modeling, right? Especially when we want to use this to estimate some effects of interest. Should we start with the model or with the effect of interest? So the classical GRM framework, at least the way I see it, is we start with the class of models, a very general class of models. Then now for specific effect measure, let's say I want to estimate the relative risk. Then you can choose the appropriate link function so that the regression coefficient will correspond to the relative risk. Or in this case, you choose a link function to be the log link. Of course, one of the main points of this paper is GRM may not be general enough to cover all the effect measures. There's very weird in shapes or may be different or when you want to model different treatments. So they come up with a much more general class of models that accommodate effect measures that are not covered by GRMs. Well, but then really, our question is, do we really want to make our models larger and larger, more and more general? Or do we really want to actually, this is the way we think about this problem. We start from the target parameters, and then we choose suitable nuisance measures to complete the parameterization. And by doing so, we achieve that the nuisance parameters here need not be the baseline risk, which is the case for both GRM and the regression by composition. So I will illustrate this with a simple example that taken from a paper by Thomas, Jamie, and myself. So this is a familiar GRM mean model for the bespoke model, where you take log of the probability as some linear term. This is equivalent to the two parts. Like the first part is the effect measure relative risk. This is the measure, the parameter of interest, arguably in a lot of contexts. And then the second part is a baseline risk, right? A lot of time we're not really interested in this baseline risk, but because we're doing this in this GRM framework, right? We often have to specify a model for the baseline risk. Also the case for regression by composition, if you start from, the first component of regression by composition is a baseline risk. Now, as we know, this GRM is very popular for modeling binary model with logistics, but if you, for modeling relative risk or risk difference, this has not been that popular, or people have some reservation about this because of the variation dependence between the baseline risk, which is the nuisance parameter here, and the effect of measure, which is the relative risk here. And these two parameters being variation dependent cause a lot of problems. But there's no reason why we have to fix the nuisance parameter to be the baseline risk, which is the case for both GRM and regression by composition. And it is the most natural nuisance parameter to all of us as humans, but not necessarily the most natural one to nature. Okay, so as one example, once we move away from this idea of we have to first specify a model class and then pick one in that class to coincide with our effect of interest, now we can start with our effect of interest, let's say relative risk. Then we are free to choose a good nuisance parameter. In this case, one particular choice is the so-called S product. Okay, so this will be variation independent of relative risk. And one easy way to see this, I'm very glad that Ren has shown this plots, that these are the contour lines for relative risk, and the red line is one contour line for the S product. And you can see that these two are variation independent, right? So basically, if I specify any value for relative risk, I'm still, I will always get a valid probability space back. This is another contour line for the S product. You can see that it still cross every single contour line for risk at one and only one point. So not only that, the R product also works for this difference. You can see this very easily. I just follow a plot. And as I just listening to Leonard's talk, these are the effect measures that are interesting, and you can eyeball it. This will work for every single one of the effect measures that you might be interested in. Okay, and the further complication, which I think Sting has already took my point, which is the regression by composition will be order dependent, right? So for example, if you have two treatments, A0 and A1, based on L0, then by switching the order of the regression by composition component, this will imply different probability models, right? These are just some visual plots to show you that this is indeed the case. So the left-hand side and right-hand side, they have exactly the same parameter values, but you can see that the implied probability plots are very different. And not only that, as they has pointed out, that the interpretations of these model parameters will also be different depending on which orders these components show up in the flow, right? So then this is a question of, do we, also I think Heather also pointed this, how do we choose the flows in this regression by composition? So I would like to conclude with a more positive note or proposition that we can actually, I mean, this is a beautiful framework, and it would become much better or even near perfect if we switch one component in this framework, which is that we don't have to start from baseline. We can start from, for example, here, let's say we are still interested in the same thing. We're interested in effect with A0, A1. Now maybe you tell me, you are interested in effect with A0, where A1 equals 0, you want to measure this in the relative risk scale. You want to measure effect for A1 where A0 equals 0 on the odds ratio scale. You want to measure effect for A1 where A0 equals 1 on the relative risk scale. Okay, you tell me like whatever measures you want, right? So this will be order independent, right? You tell me the three effect measures that you want it to be, you want to estimate. Now I tell you, I will complete the parameterization for you with a generalized R product. This thing will be variation independent of all the three that you tell me. Okay, so it solves the variation independence problem, and it also naturally solves the order independence problem. Right, so it's still Lego blocks, but now you are allowed to build your Lego blocks in any order you like, and they don't conflict with each other. And once you add more Legos to your stuff, it doesn't change the original ones. Yes, this is the last slide. So final message, start with the parameter of interest, construct a model around it, then we'll solve almost all the problems we see.
I apologize that we're running out of time. We have time just for the final person who gave their name before, Andres Rakar from Josef Stefan Institute. I'll wait for a very quick comment. Again, apologies that we have slightly run over. We will start wrapping up soon. You don't have slides.
Okay, so thank you to Adam. Thank you to all. My comment was done yesterday, so I don't have slides. I will just shortly read it. Congratulations, naturally, to all the authors on a very interesting article, an application of group theory to probability and statistics. So it exists, to my opinion. There are many authors very involved in causal inference, but I think it would more belong to algebraic methods, algebraic statistics related approaches. So firstly, I wanted to point to a need in the article of a more concise mathematical definitions of what you actually do, because group action as such so is commonly defined, I would say, as applying some transformation from underlying groups on transformations or maps themselves. But group as concept is super large, so you could have semi-groups, you could have rings, semi-rings, fields, you could have many areas, Galois theory, representation theory, which was a lot mentioned. So you mentioned category theory, some concepts from algebraic geometry. So my personal view and advice is to be much more concise on what this group action really is, yes, such, because you multiply on the right with certain so mathematical objects, mathematical things, but commutativity was mentioned, associativity even in the demo and so on. This could be non-commutative, ordering was mentioned, then you would have probability was mentioned a lot of times, even you go to free probability. How to use this when you would study this probabilistically could be a very interesting aspect, but I think that this mathematical aspect, it's interesting, but a bit vague. It could extend to many, many things, but it seems that you address very specific things. So this would be really great to define much more adequately and limit it to probably certain group actions. And also you mentioned vector spaces in the general article, also affine spaces, but also here probably some more limited and more specific vector spaces. Very, very wide concept. As we know, you have Hilbert, Banach, and a lot of other things. This also would probably need more concise definition of which spaces are addressed by these mathematical transformations. Secondly, so this relates to what I mentioned, how to include this to interesting probability perspective. You mentioned optimal transfer with push-forward measures on one place in the article when you combine algebra and probability, which is the essence probably of this article. In probability, there is free probability that combines this nicely, operator algebras and things from probability as such, random matrices. So it would be interesting what to include here. There was even a thought of mine, Langland's program combines some of these things. Daring, but maybe this could even be included to explain some things related to statistical models that you address. Langland's program is separate from mathematics, naturally. And thirdly, as we mentioned, there is naturally half-year program at Cambridge University at the moment in causal inference, and several authors from you are extremely or all active there. But question here that brings to my observation is this necessarily connected at all to causal inference? Naturally, you addressed, you mentioned this, I would say, more potential outcome perspectives. To my thought, when I read it, I think that one of the discussions of present time in causality research is unification of causality. So how to really use this perspective in more general, I would say, causal models. I think that Professor Richardson is there. There is single world perspectives there. There is do calculus with graphical models. You even have Poe calculus, I think, related to this. So it would be highly interesting, probably, how to combine these perspectives from algebra, in this case, if you reach group theory, to use it in the present day developments of causal research for these mathematical foundations of causality. This could probably be highly interesting. Thanks a lot.
Thank you. So I apologize, we have run out of time to accept more discussion contributions today. I didn't want to, there were lots of great discussions today. I didn't want to cut people off. I'm not in a spirit of censorship, so I wanted to make sure, you know, that everyone got their time, but the price of that was we can't accept more discussions. However, despair not, because we can still accept contributions in writing for those of you who would like to say something on this paper. That will be published along with the journal, and around a month or so, 21st of April, the details are on the RSS website, but I think journal@rss.org.uk is the email. I've remembered it correctly. So I don't want to talk longer because we've run over, but there is one final thing to wrap it up as we reach the end of this discussion meeting. I'd like to call on the author and or co-authors to reply if they wish for up to 10 minutes, and you have the floor for that. But this part is entirely optional as per tradition, because you will, I suspect, like to give a more considered reply as well in the journal with some time to discuss with your co-authors later in the journal. But if you'd like to make some comments now, then you're more than welcome.
I'm going to try and keep this under 10 minutes, which probably means it'll be 20. No, I'd like to start actually by where I started earlier, which is reflecting on the refereeing process. We had one really positive referee, which is probably the reason we're all here today. I think minus that one really positive referee, we wouldn't be. We also had referees who were who saw balance, and then we had some who were critical. I think that we've had a similar thing with this discussion, and I want to reflect that we were grateful with the refereeing comments, and that gratitude increased with time as we fully understood what people said. And then we understood what we were trying to do better. So I am enormously grateful to all the discussants, both positive and otherwise. And I predict that will grow with time. I'm going to attempt a couple replies to a very small number of things. And I might ask some of my co-authors to help on some aspects. Stein, you give this notion of compositional grammar, but also that we needed some syntax. I just want to absolutely agree with you. We fit these models. Sometimes they work, sometimes they don't. We don't really understand when that's going to be the case. So I absolutely agree. A grammar needs a syntax, and I think that's a really nice way to put it. What did I want to say next? To Peter. I think, where are you, Peter, there? I think we agree on the importance of sampling consistency. The reason I say I think is I'm not totally sure I understand it, but I absolutely agree that what we want to do is induction. We want to go from a small group of people beyond. And I love the idea of formalizing that, because it is the starting point and we can't go anywhere. There's no point in us attempting to learn anything from me about you unless we can do induction. So that is absolutely critical. So, and if I understood it better, I could say more, but I'm confident that we agree fundamentally. A sort of smaller point, you mentioned about not modeling correlations. You know, I started out doing longitudinal data analysis. That would just be unthinkable to not model correlations in that setting. So again, totally agree. It is interesting to think about what happens if you don't start with an independent structure, but you start with, well, okay, let's say you do start with a multivariate normal distribution that is independent, but then you want flows that induce dependence. That's a really interesting idea, and we have thought a tiny amount about it. And one of the challenges, as I was discussing with somebody after the demo, is to maintain vector space actions on something that is, when you're talking about matrices and matrix multiplication, sort of inherently non-commutative. So it becomes quite difficult to maintain that. And whether you can build up the required complexity from a series of vector spaces or not, so whether you need something more general, it's a good question, but unambiguously, we agree that you can do better with modeling longitudinal data as these are than we did. Let's see, Stephen, the idea of preferring original scales, absolutely agree. It's actually one of the things that has most motivated what we wanted to do. So just to give a simple example, and my dad actually mentioned this as well, somebody once said, and I can't remember, you know, the first law of applied statistics is take logs. And I want to scream no to that, because actually understanding things on the original scale, it's easier to have those conversations with scientists when we're not talking on a log scale. So the idea of not doing, well, we'll take logs, assume a normal distribution and do whatever, but start with a log normal distribution and do things to that seems to me, to all of us, I think, a really attractive idea. So agree entirely about that. Heather, you had an interesting comment about mechanistic models necessarily constraining probabilities to 0, 1 to the, and that sort of makes sense, right? Frian, I wonder whether you wanted to talk anything about the way that you can generate sort of affine models while still constraining to 0, 1. Do you want to say anything about that? Yes, indeed. Yes. Okay.
thinking about that.
Yeah. Maybe that's something just to say we have thought about that, and it's not necessarily as impossible as it might seem. Okay. Dad, thank you for the idea of emphasizing distributional comparisons. I do think that's the essence of what we're trying to do. And I think it sort of links back to things Stein was saying about sort of emphasizing distributional comparisons, and this notion that parameters are not going to be easy to interpret in isolation. That even though it looks like it's part of a simple component, the interpretation of other components, in a way you were both talking about this, may have a bearing on what this final parameter means. So I think it's a really important point. Limbo, we love the odds product. And we look at it and we see it's almost like a sort of anti-flow, because it goes in the other direction. And we keep wondering about to what extent it can be seen as a complement to this idea. So we would love to explore this further. It seems so attractive, the way that you can gain, as you've described, sort of things that are guaranteed to remain probability models. It's a beautiful notion. And then, Andre, you were talking about the need to be more concise with our definitions. That's the whole objective of mathematics, so I agree. But you were also thinking, well, can we be broader in our constructions? Should we think about semi-groups and monoids and so on? And I think that's a very interesting question. There is so much to be gained from restricting to vector spaces. You can do differentiation easily, so likelihood maximization, but as always, simplicity should not be at the cost of relevance to the real world. So I think we should think more broadly about these things than we are currently. It is admittedly a very simple setup. I have to say I did not expect any mention of the Langlands program in response to this. So I feel honored to even have that mentioned in this session. Do any of the co-authors want to say anything? Mats, please. Yeah, of course.
First, thank you everyone for engaging with the work in such a lively and active way. I would just make one comment that touches on some of the discussants' claims. So in particular, first with Stein, I agree that there are subtleties by which how to interpret this model. For example, the order by which you include the Frost matter. And Limbo and Heather were pointing to similar things. And there I would say that it's not necessarily so that you motivate the model by including terms one by one, and that's how you come up with the model. That was not, for example, how we came up with the Michaelis-Menten model. We tried to come up with a simple parsimonious parametric model that would give us the Michaelis-Menten model. So this is a different perspective on the whole game. And I think that also fits well with Stephen Sand's comment, which was, this is in pharmacology, this is a model justified by biochemistry, by pharmacological theory. So the idea is not necessarily to come up with a sequence like this out of the blue, but rather justifying a parametric model in a parsimonious way. And this relates also to causal modeling. So Sakar, you mentioned in the last part, is there any relation to causal modeling? Many causal models are parametric model. Let me mention one, marginal structural models from Robbins, presented in 2000, more than 2,000 citations as well. That is a parametric model for a causal quantity. Why don't you fit that with a different model than what you usually are doing now? Now you have different ways of fitting it. The third point was to Professor Farrell. So thanks for engaging with us as well. I really like that point, because I think very often, and that also relates to the other points, and also Limbo's points, he said, oh, I want to interpret the coefficients as what I want, but I never said I wanted the coefficients as my primary target of inference. That could be something else. It could be some marginal parameter, or it could be some other conditional parameter that you derive from the distribution. So a functional of the distribution you've already fitted. So yes, then we cannot interpret our betas in the way in a very simple way, but we can transform this to something that has an interpretation. And then I think many of the problems are kind of less severe. I'll end there.
Thank you all. So yeah, that's the end. So full details of all upcoming discussion meetings are available on the RSS website and announced in members' newsletters and on social media. If you'd like to receive an invitation to future discussion meetings, then email journal@rss.org.uk, the same email that you submit written discussions to, and we'll add you to our discussant mailing list. And yeah, thanks to everyone for joining the meeting today in person and online. For those here at Imperial, we can now move to the common room, room 549 on the 5th floor of this building for a drinks reception. Just follow people. Maybe if you're online, crack open your own bottle of wine. And you've earned it, and we made it to the end. So thank you to everyone. And thank you to Heather for really being instrumental in organizing this meeting, to Heather Batley.